And it's an exciting time. And again, we have great science around it. We're pushing our partners. We're pushing NASA. We're in a second space race right now. The Chinese want to get back to the moon before us. That's not going to happen. America has led in space in the past, and we are going to continue to lead in space in the future. And again, this discovery today, I hope makes everyone excited about the future missions that we're going to have and the exploration we're going to do and the science we're going to develop to make sure we can send Americans, mankind, throughout the universe. And so, but we do want to lean into this exciting news that we have today. And to give us more, I'm going to turn it over to Nikki Fox, who is the Associate Administrator for our science mission. Nikki.
Thank you so much. Thank you. Yes, it really is an exciting day today. NASA, what we do is we study the seemingly impossible. That's what we do every day at NASA Science. And NASA Science is undisputably the global authority in the search for life beyond our home planet. And so today we are going to talk to you about this amazing, exciting discovery. And I also want to make sure that we put context around it. And you see like how it fits into our search for life in the universe. Our galaxy is 100 billion light years across. And within 10 light years of Earth, there are at least 400 known planets. And that means there is a possibility, some would even say a probability, of life beyond Earth, including maybe even complex intelligent life. And today we are really showing you how we are kind of one step closer to answering humanity's one of their most profound questions, and that is, are we truly alone in the universe? So if I could have the first image, please, that would be great. So last July, as Secretary Duffy eloquently described, NASA's Perseverance rover found a leopard-spotted rock at Mars. And scientists immediately knew it was interesting. We hadn't seen anything like that before on Mars. And we talked about it last summer. The moment we found it, we put out the images for everybody to see and everybody to share in the joy of NASA science. And, you know, today, we're really here celebrating that incredible hard work of the science team as they literally tried to prove it wasn't interesting. Maybe it's just something else. Maybe it's not, you know, the key result that we've been waiting for. And so they've done the analysis on these leopard spots, and we think they are potentially made by some sort of ancient life. This finding by our incredible Perseverance rover is the closest we've actually come to discovering ancient life on Mars. And if you can't tell, we're really excited about that. But, you know, I want to put it into context. It's a signature. It's a sort of leftover sign. It's not life itself. And it certainly could have been from ancient life, and that would have been something that was there billions of years ago, nothing that's current there. And, you know, it could certainly, as we say, be made by ancient life. And what that means is we look at everything we know about life on Earth. And this is the kind of signature that we would see that was made by something biological. In this case, it's kind of the equivalent of seeing like leftover fossils, you know, leftovers from a meal, and maybe that meal's been excreted by a microbe, and that's what we're seeing in this sample. And, you know, again, as Secretary Duffy said, we don't know for sure that's what it is, and we won't stop after this first analysis. This certainly is not the final answer. But we have this first result, and we're sharing it with you, the world, and we are asking you to look and give you our analyses also. And that's what we do in NASA Science. This is, you know, how we find our information. It's part of that long journey. We ask a question, we design a mission that can actually go and address that question. We develop the technology, we build the hardware, we launch it into space. It takes the data, it brings back the information that we need here, we analyze it, and we come up with answers to those really, really tough questions. We've actually been studying Mars with, even as early as 60 years ago when we sent our first missions there to take pictures of Mars and tell us really that's quite an interesting place and we really do want to send humans there. And so we've been doing this so we can understand the planet so we are ready to send our humans there. We certainly, as we look forward, we plan to send more missions to Mars in support of the Artemis program, which we're really proud of. And it will open the door for humans to study and better understand the red planet and perhaps even one day bring back Martian samples home for us to actually study here on Earth. And I want to underscore the point that NASA's science discoveries do not just happen at random. They are the rewarding results from meticulous, long-term strategic planning. We send these missions to really address these incredible questions. And each new discovery helps us just, kind of drive what research is coming next. What missions do we want to design next so we can kind of take that full bench of tools with us to solve the problems of how best to support, to explore our solar system. First with robotic missions and then with humans. And before I pass it on to my colleagues who are going to tell you all about this incredible, the details of this incredible finding, I just want to talk a little bit more about how NASA searches for life. And there's so much happening that I am incredibly excited about. We have Europa Clipper that is on its way to explore an icy moon of Jupiter to investigate whether the subsurface ocean underneath that icy crust has the potential to support life. After that, we'll launch Dragonfly, which has been deemed the most exciting science space mission of your lifetime. And it's a drone, it's the size of an SUV, and it's going to be humanity's first airborne science mission to another world. Dragonfly will explore the amazing world of Saturn's moon Titan, which is the only place in our solar system where that have lakes of liquid on the surface. And with Dragonfly, it's going to let us understand the prebiotic chemistry that predominated Earth here before the origin of life. And the other thing we're looking for all over the universe is potentially habitable worlds. 30 years ago, we first discovered an exoplanet around another star system, and today we know of thousands of them. This has changed the very way that we look at our night sky. We know that there is, on average, a planet for every star in the sky. And as I've been saying, each new mission is specifically designed based on all of the knowledge that we've gained so far. And in this case, the knowledge is allowing us to lean forward to study a concept mission that is supported in the President's budget called Habitable Worlds Observatory. And that will allow us to search for habitable worlds and for signs of life around 100 of our nearest stars. Super, super exciting. Mm-hmm. From its vantage point in deep space, it will observe a variety of critical targets for us to go and explore, for us to sort of put our fleet of telescopes staring at those, including our amazing James Webb Space Telescope, and of course our upcoming flagship mission that we launched in 2027, the Nancy Grace Roman Space Telescope. Super excited, yay Roman. The Habitable Worlds Observatory insights could help keep astronauts and human infrastructure safe in space, and it will be the most powerful telescope NASA has ever launched, maintaining Americans' leadership in space, which is so important. But for now, back to the present and back to Mars. And so I am delighted to turn it over to Dr. Katie Stack-Morgan to tell us more about Perseverance's work on Mars, and she's joining us by phone. Take it away, Katie.
Thank you so much, Nikki. The discovery of a potential biosignature or a feature or signature that could be consistent with biological processes, but that requires further work and study to confirm a biological origin is something that we're sharing with you all today that grows from years of hard work, dedication, and collaboration between over 1,000 scientists and engineers here at the Jet Propulsion Laboratory and our partner institutions around the country and internationally. A discovery like this comes from years of strategic planning and science analysis from both the Rover team as well as the Mars community as we went from the development of the Mars 2020 mission as a concept in response to the priorities of the Planetary Decadal Survey, to the landing site selection, and now to the daily operations of the rover that provide us such a fantastic data set that we're going to share with you today. If we could bring up the first image here, I'll be providing some overall geologic context for the discovery of these leopard spot features. The Perseverance rover landed in Jezero crater in 2021, and this site was selected as the result of a multi-year community effort because we decided that this site was truly the best place to accomplish the Mars 2020 mission goals of seeking signs of ancient life on Mars and putting together a collection of rocks for possible return to Earth in the future. Jezero was selected because it's in a location amongst the most ancient terrains on Mars, exposing some of the oldest rocks anywhere in the solar system. And these really ancient rocks provide us a window into a period of time that's not particularly well represented on our own planet Earth, but it's a time when life was emergent on Earth and could have been on Mars as well. Jezero is also indisputably the site of an ancient lake, which we know because we have two river valleys entering into the crater and a river valley exiting the crater through which water flowed out of the crater. During the first 4 years of the mission, Perseverance explored three main geological terrains within the crater. The rover landed on the crater floor, which was a sequence of igneous rocks, including lava flows and igneous cumulates, that had a number of interactions with water and preserved probably micro-environments that were likely habitable. The rover then transitioned to the western fan. It's a sequence of sedimentary rocks whose sediments were transported from ancient terrains out of the crater into the crater in a relatively long-lived and stable lake, delta, and river setting. The rover then transitioned to what we call the margin unit. This was a thick sequence of igneous rocks that really distinguish themselves by strong orbiter spectroscopic signals of the minerals olivine and carbonate. After the margin unit exploration, the rover had a chance to traverse into the Retva Vallis, which is the main feeder river valley that once fed the ancient lake that was present in Jezero. And this river valley, more than 3.5 billion years ago, this valley would have been filled with rushing rivers carrying mud, sand, and gravel from outside the crater into the lake inside the crater. This kind of energetic setting was probably punctuated by periods of calm when water would have backed up, creating a relatively low-energy lake environment where deposition by settling from suspension could have occurred. Eventually, though, this water dried up, the lakes and rivers dried up, and the Bright Angel outcrop was revealed. And this outcrop records for us a potential habitable environment that we can study and the rover can explore on the surface of Mars today. If we can bring up the next slide, please, we can see Bright Angel through the eyes of Perseverance. It's a distinct light-toned outcrop, and its current extent and relief has been exposed to us through billions of years of wind, erosion, and thermal cycling. The rover spent several months exploring this area, ultimately pushing to the northern edge of the channel where the Bright Angel formation met the margin unit. And it's here at the contact, this edge of the river valley, that the rover explored a special target called Chayava Falls. If we move to the next image, please. The Chayava Falls rock and those around it show very thin layers. They're often red to tan in color, and they're very fine grained, so the sediment that makes them up is very, very small. This, coupled with the fact that these rocks occur in a river setting, really points to a sedimentary origin here, where we had deposition of these sediments in water. Here in this area, we also have some coarser-grained rocks, again suggesting that we had a transition from these more energetic river environments to the more calm lake environments. And while every outcrop on Mars has an interesting story to tell, in order to really understand what makes this particular outcrop so special, we have to get our noses to the outcrop, or in this case, the rover's arm, up close and personal to take a look at all the details of these rocks. So to tell us more about that, I'm going to pass it on now to Professor Joel Hurowitz, who is the lead author of the study that came out in Nature this week. Joel, over to you.
Thank you so much, Katie. If I can bring up the first view graph. What you're looking at here is a selfie that Perseverance took of itself in front of the Chayaba Falls workspace in the Bright Angel Formation. And I show this image, one, to kind of provide a little bit of additional context and show that we collected a sample from this rock. You can see a hole in the rock where that sample core was collected. But also to make the point that we really used every scientific instrument available to us on the payload to investigate these rocks and really try to tell or paint as complete a picture as we can of what these rocks are made of, the environment they were deposited in, and how the interesting features that we see in them might have formed. So what I'm going to do now is I'm going to move to the next image, and we're going to zoom back up to the surface of the Chayaba Falls rock. And this is the same image you were looking at before. And what I want to do with this image here is I just want to convey some of the excitement that we had when this image came down last summer. And what we saw in this rock were these layers of very fine-grained, rusty red mudstone that had in them these incredible features, these things that we took to calling poppy seeds, which are the sort of dark black spots in the rock, and leopard spots, which are these kind of ring-shaped features that have dark rims around them. These textural features told us that something really interesting had happened in these rocks. Some set of chemical reactions occurred at the time they were being deposited. And so we really wanted to understand what those reactions might have been. And one of the things we wanted to ask ourselves was, is it possible that organic matter might have played some role in the generation of these textural features? So we turned to our organic chemical detector, the Sherlock instrument, and trained it on this rock at the location of those two little black boxes that you see on the surface of the rock. And I'll switch to our next view graph. The data that we got back from the Sherlock instrument was fantastic. What you can see here is a set of spectra that are called Raman spectra. And there's a lot of information on these graphs, but the key thing to take note of is the fact that what we see in these spectra is something called a G-band, and that's pointed out on the image. The G-band for us is a smoking gun indicator for the presence of organic matter in this mud. And we see that G-band in the Chayaba Falls target, and we actually see it in a couple of the other locations that we interrogated around the Bright Angel Formation. And this tells us that we had a rusty red mud that was deposited in the presence of organic matter. So the next question for us was there some reaction occurring between the mud and the organic matter to give rise to those interesting poppy seed and leopard spot textures that we were seeing? So we turned to the other instrument out on the end of the rover's arm called the Pixel instrument. And the results from that instrument are shown on my next slide. Here what you can see is the chemistry of the surface of this rock rendered in three colors, red, green, and blue. And the mixing between colors is telling us something about where elements are present together. What I'm showing you here is that the mud itself, which shows up in red in this color representation, is rich in iron. The things that are purple are rich in the elements iron and phosphorus. And that iron and phosphorus shows up in the poppy seeds and in the rims of those leopard spots. In the places where you can see sort of dull yellow to green tones, that's where iron and sulfur have been combined together in the cores of the leopard spots. And they have been combined into an iron and phosphorus-bearing mineral that we think is vivianite, and an iron and sulfur-bearing mineral that we think is a mineral called greigite. And what's exciting about these finds, this sort of combination of mud and organic matter that has reacted to produce these minerals and these textures, is that when we see features like this in sediment on Earth, these minerals are often the byproduct of microbial metabolisms that are consuming organic matter and making these minerals as a result of those reactions. But there are non-biological ways to make these features that we cannot completely rule out on the basis of the data that we collected with our rover payload. So what we need to do from here is to continue to do additional research in laboratory settings here on Earth and ultimately bring the sample that we collected from this rock back home to Earth so that we can make the final determination for what process actually gave rise to these fantastic textures. So with that, I'm going to close out, and I'm going to turn it over to Dr. Lindsay Hayes for the next part of the program.
Thanks, Joel. So in order to wrap us up, I really want to highlight some context for the points that we've made here today. First, we are excited. We're excited to be announcing the publication of this peer-reviewed paper about these features from this about 350 billion-year-old rock on Mars, right? This is about the same time as we see some of the earliest fossils of life on Earth. And so these features are helping us to better understand the potential biological history of Mars. After our announcement last year, the peer-reviewed publication is the next step in the scientific process, and it allows NASA to make the data that we collected from this mission and the science team's interpretation of that data sort of available to the broader science community for further and wider study. This work to investigate the processes that are described here will continue, and hopefully, eventually, this will be followed by the delivery of these samples back to Earth, where they could be studied in terrestrial labs. Additionally, I want to remind everyone that what we're describing here is a potential biosignature. That is a characteristic, element, molecule, substance, or feature that might have a biological origin but requires more data or further study before reaching a conclusion about the presence or absence of life. And then finally, as we have explored Mars, one of our main goals has been to determine if Mars was habitable in the past and whether or not life was ever present. This was part of the reason that we sent Perseverance to Jezero Crater. And the findings that we talked about here, they weren't an inevitable result from this mission, right? They're the direct result of more than decades of work by tens of thousands of people with many different missions that were meticulously and strategically planned, that payloads that were developed and missions that were executed capable to lead us to achieving this discovery. Our exploration themes, and I think there's a slide here, have guided the Mars exploration program as it has evolved over time. And these are the reasons why we explore. These missions have expanded our understanding of Mars to more than we know about any other planet other than our Earth. And it's, examples of our combined ability to look at things that allows us to look at things like this Martian meteorite here, which is EETA 79001. This is a Martian meteorite that was found in Antarctica, but combine these kinds of work, the curation of these meteorites, the study of these meteorites in NASA labs, with data from our missions like Viking, allowed us to characterize this meteorite and a whole host of other meteorites as coming from Mars, which allows us to do some additional context with our missions. So all of that combined work, right, there's no other space agency that has conducted such a long-term coordinated campaign in planetary exploration. This demonstrates American leadership in space and in science, and data from these robotic explorers are now feeding forward to our plans to prepare humans to return to the moon and to go onto Mars as part of the Artemis mission. And so thank you very much, and I'm going to send it back to the moderator for time for questions, I believe. Thank you very much.
Thank you so much to all of our speakers today. We are going to move on to the question and answer portion of today. As a reminder to the media, you can hit *1 to get into the queue. We were planning to take one question per person. I also want to make sure you know we do have imagery available, the imagery we showed, as well as some animations that we did not. If you go to nasa.gov, you'll be able to see our press release, and you will have access to imagery there. With that, we will go to our first question, which is from Marcia Dunn with the Associated Press.
Yes, hello, good morning. For someone at NASA, what's the latest on NASA's plans to retrieve the samples from Perseverance? Has NASA made any decisions yet on the options put forth by former administration Nelson before he stepped down? Is there any kind of tentative timeline? Thank you very much.
So, listen, we're looking at how we get this sample back or other samples back. What I said at the start was this is 30 plus years of exploring Mars, and that is going to continue into the future. This is exciting news. What we're going to do is look at our budgets. We're going to look at our timing, and how do we spend money better, and what technology do we have to get samples back more quickly. And so that's a current analysis that's happening right now. Again, what is the best way to do it, which is what we're looking at and thinking through at the moment.
Thank you so much. Our next question is from Bill Harwood with CBS News.
Yes, hi. I'm curious. One of my colleagues, Miles Doran, found a YouTube video from back in April that basically highlighted this very formation and talked about it being a possible biosignature. I'm just wondering what's changed since then to warrant raising this to the level of a news conference. Was it simply the peer review process running its course? Because it really sounds very similar to what you guys reported back then. Thanks.
Joel?
Does Joel want to take it?
I think Joel should talk about it since he's the author of the amazing paper.
Yeah, I'd be happy to, Bill. Thanks for the question. What has happened in the interim between last summer and now is a variety of things. One, the continued exploration of Nerette vivalis so that we could collect more data from this locality and better understand the environment that these rocks were deposited in and really sort of firm up our understanding of what type of setting they were formed in. It allowed us to gather more data on these features that we have called potential biosignatures so that we can better understand the nature of the reactions that might give rise to them. And then, of course, after a few more months since that last press conference of collecting data, there's a long period of sort of aggregating and interrogating that data and writing it up and putting it together into a comprehensive publication that then has to go through the peer review process. And so that has all been going on sort of in the background between last summer and now. That is what has happened between then and now. And I would highlight that the peer review process is a really important component of being able to present these results here to you today.
And Bill, that's part of the process, right? So again, we find the sample. We can have a lot of commentary that agrees with what NASA has found. Some may disagree, but to interrogate the data, as Joel just mentioned, and to have it peer reviewed. What's exciting is in the past, what we thought it was, our peer reviewers would say it was not. Our peer reviewers are saying, well, this actually could be what NASA thinks it is, and that's why this is so exciting, and that's why we want to have this press conference to share it with the world, to share it with you. And also, we are ultra transparent, right? If we had this exciting news about the peer reviewers and what we think we found at NASA, and I didn't bring it to you, if we didn't have everyone here together, you might go, you're trying to hide stuff from us. Why didn't you tell us that a year ago? So we are here to say, this is exciting. And we want to share that news with, the data that's been pressure tested with other scientists who are like, this could be very real. Anyone else want to?
No, you nailed it. Yeah.
Great answer. Thank you so much. Next, we have Ken Chang with the New York Times.
Hi, thank you. So this is for Secretary Duffy. I've talked to a few scientists about this, and they all say it's very interesting, but that there are potential non-biological explanations for these minerals, and the only way to really find out is to bring them back. But the Trump administration, in its budget request, called for the cancellation of the Mars sample return mission. Based on what Mr. Duffy said earlier, is that not the case anymore? That you are still looking to possibly conduct that?
So we have to look at all of our missions, and we have to look at the cost and the time on each of the missions that are going to be deployed and have been deployed. And because we care about resources and we care about the time frame, we believe there's a better way to do this, a faster way to get these samples back. And so that is the analysis that we've gone through. Can we do it faster? Can we do it cheaper? And we think we can, and that's why we're not going to take it back on Percy. We're going to actually figure out a different way to bring it back. Again, and we think we can do it faster and more cost effectively. But again, I want to be really clear. This is a 30-year process that NASA has undertaken. President Trump didn't say, hey, let's divert, let's forget about Mars. No, we're continuing our exploration. And by the way, we've been very clear under this president that we don't want to just bring samples back from Mars. We want to send our boots to the moon and to Mars. And that is the work that we're doing. So, and by the way, Ahmed has even said, maybe we'll send our equipment to test this sample to Mars itself. all options are on the table, but again, we're gonna use the best options possible to do the best analysis possible to give you the best information possible.
All right, then, I will move on to our next question, which is Irene Klotz from Aviation Week.
Thank you. For Secretary Duffy, do you expect this finding will shuffle the administration's priorities for returning the samples? And for Joel or Katie, what else can be done remotely to better ascertain if the mudstone organics are biologic or abiotic? Thank you.
If Joel and Katie want to go first, I'll answer that second.
Yeah, I can take that one. Thank you. While we were exploring the Bright Angel area, we basically threw the entire rover science payload at this rock. And so, we're pretty close to the limits of what the rover can do on the surface in terms of making progress on that particular question. And of course, that was by design, since the payload of the Perseverance rover was selected with a Mars sample return effort in mind. So the idea was for our payload to get us, just up to the potential biosignature designation and have the rest of the story told by instruments here on Earth. We are still in the midst of analyzing the geologic context of this sample, and our scientists are continuing to do the work there. Joel's paper represents, I think, kind of the overview and summary of our understanding, but we have other scientists on the team who will be putting out works over the next year or so, digging more into these details. So I think we'll learn more about the geologic setting of this sample and what that may mean for its potential astrobiological potential. And so that work will be ongoing. But I think in terms of what we could do with the rover, we threw the whole payload at it, and the result was this exciting discovery. Joel, let me know if you have anything you want to add.
No, you nailed it, Katie. Thank you.
If I may add one other
Sure.
thing as well. And I'll also add, of course, as we said, as multiple folks have said today, the other really important thing about this, and this is a stage in the scientific process, right? It is not just what else can we do with the rover, but what else can different scientists, around the world and, within our American science and laboratories and such, be able to do and analyze and find and explore and understand more what other potential causes there may be for this type of signal. So it's the rover, but it's also, the broader science community as well. Sorry,
so, thank you. In regard to, does this change the mission? I would say, no, listen, we are about manned exploration, human exploration. But as part of human exploration, you need science. Right? And so what we do on Mars, these missions help us in what we're going to do in the future as we do go back to the moon and eventually get to Mars. We study our own atmosphere to learn from what we have here on Earth in our atmosphere, what we can learn about other atmospheres potentially in our galaxy and beyond. And so, no, this is consistent with the President's vision and mission of continuing the science to support human exploration beyond Earth.
All right, thank you very much. Some interesting answers. Next up, we have Andrea Leinfelder with the Houston Chronicle.
Hi, you began this news conference talking about, past discoveries that might have suggested life on Mars, but ultimately were something else or could have been something else. Can you run us through some of those again? Thank you.
Sure, absolutely. I mean, of course, there is the ALH 84001, which was an understanding of a meteorite that we found that had some very interesting signatures. Going further back, there was the Viking data and trying to understand exactly how to interpret that data. But what I want to highlight, and this is something we've talked about a few times here, we think about these things and we try and frame these things in a way to communicate different ways of what each of these detections are, right? So the first thing that happens, right, is that you detect a signal that can result from biological activity. You want to make sure that it's not contamination. And then you try and understand that signal in the context of the area, the context of the environment where you found that signal. And so one of the things that we're doing here is, as Secretary Duffy said, we're trying to be very transparent, right? What we did is originally we announced that we had found a signal. This paper is showing that, we understand the context of the environment around it. And, we sort of, as we think about these things, we want to be be clear what we are communicating here, and that the next stage is to communicate and to see what the rest of the science community, right? These discoveries may become more significant as more data comes in from other research. Other science may show that there's other ways to create a signal like this. But as we change these things over time, we're showing that we're more and more excited about this as we learn more and as we've understood more.
All right, we are looking at probably about 2 more questions, but we are certainly trying to get through as many as we can. For anyone we don't get to today, definitely we'll ask you to send us notes and we will follow up. But going on, our next person is going to be Eric Berger with Ars Technica.
Hi, thanks very much. A question for Secretary Duffy. We talked a little bit about Mars sample return, and obviously there's some interesting things to study on Mars. China is planning to launch the Tianwen-3 mission to return samples from Mars in 2028. Does it concern you that China is likely to be in a position to accomplish this before NASA?
So first, Eric, I love you guys are all asking me questions. We got some of the brightest people at NASA with us. I'll take them. I was hoping your questions were going to be more on this exciting news that we have today. But listen, we're running our plan, right? We're making the right calls for America and for our partners. And again, we lead, and we are going to continue to lead. But it's always important that we keep pushing. We have to push because we are in another space race. And what I don't want to do, and we work very well together. I want to make sure we're making the right decisions, right? And I have to look at dollars, and I have to look at time, and I have to look at return. And as we do that, we thought, well, there could be a better way to do this to get these samples back. And I again, just to continue with missions that I don't think can meet budgets and timing, I think would be foolish on my part, because across government, every government, not just the U.S. government, resources are precious. And we are going to use our resources to the best possible abilities to advance our missions the furthest. And I would just tell you, there's been a lot of conversation on science. Science isn't going away at NASA. We are leaning into the science because we need it to make sure that we're successful on our missions to the moon and to Mars. And we have Earth missions as well that have been mandated by Congress. That is part of our science. But again, if I've been given an ask for spending a little less money, I think we can do that. I know we can do that. But I've told the team at NASA, if we don't have the resources for the right missions or the right people, I will go to the president, I'll go to the Congress, I'll ask for more money. But I feel pretty confident that with the money that we've been given in the president's budget, we can accomplish our mission. It might be a little more focused, right? It's on human exploration, but we can accomplish that mission. And again, I have fully committed that I would ask for more if I needed it. And by the way, the president loves space. He asked me about it, which is a unique position to be in as the acting administrator, but also to be the secretary of the Department of Transportation, that I get to interface with the president quite a bit. I give him updates, how it's going, what we're doing. And he doesn't brush me off. He wants to know. He's excited about this. And so if there was an issue with resources, I would go to him, and I'm sure he would support us. And I'm sure, listen, what's interesting too, and this has been great to see, this is bipartisan, right? There's a lot of fights that you all see in Congress. This is one space, no pun intended, or maybe the pun was intended, that you get bipartisan buy-in. People get excited about what NASA does as Democrats, independents, and Republicans. Everybody kind of loves it. And they would also respond to us, I think, in a positive way, should we come to them and say we need resources for something in addition to what we have the money for today. So, no, the mission hasn't changed. And we're going to continue to forge on, and I feel very confident that we can do that.
May I add?
Yes.
I want to pull on the thread that is, at no point has this administration said we don't care about samples. You know, we brought back samples from the OSIRIS-REx mission. We opened those recently, and we found amazing things from that asteroid Bennu. Look at what we've done with the samples from Apollo. We recently opened samples that hadn't been opened. They were curated, and they were, we opened them, and we've been able to study them with unprecedented machinery and instrumentation that we have here on Earth that did not exist when we first took the samples from Apollo. So it shows the value of these samples. And these samples are carefully curated. These are not just going there and picking up a rock and bringing it home. These samples are precious. We want to make sure when we bring them home, we bring them home right.
But just by the way, they're very cool samples, and they are precious.
They're precious.
We do have to work on the naming of these samples. There's, I don't know what, TTI J21, I'm like, whatever it is.
Leopard spots.
Leopard spots. We can do a little better name on the naming front.
All right, I said we'd do just one more question, so we're going to sneak that in again to the media online. Please do write us emails. We will follow up as needed. But our very last question for today will be Jeff Faust with Space News.
Good morning. Probably a question best for Dr. Hurwitz. You mentioned that there may be possible non-biologic explanations for the features you're seeing. I wonder if you can elaborate on what those might be, and if you could be able to distinguish between them short of having the samples back in a lab on Earth.
Yeah, thanks for the great question. So we actually go into this in some detail in the paper. What we think is possible is that the mix of ingredients that went into this mud, or into this rock, the mud and the organic matter, if combined under the right conditions, could result in chemical reactions that could produce the minerals that we see in the absence of biology. And really, I'll just highlight one of them. The iron sulfide mineral I described, called greigite. One of the ways that you could combine the organic matter and iron and sulfur from the rock together and form that mineral would be to heat the rock up and basically sort of cook those ingredients to produce that new mineral phase. One of the things we sort of struggled with, I don't know, maybe that's the right way to say it, but we looked in as much detail as we possibly could to try to understand whether these rocks actually showed any signs that they were cooked. And within the sort of capabilities of the rover, we weren't able to make that determination. They really don't look like they had been heated to the temperatures that might be appropriate to that type of reaction. But it is a pathway, and I think it's one that we hope that the research community will take these results and go off into laboratories and run experiments to try to recreate these features under a variety of conditions, both biological and non-biological, to see, what are the options here for making these things that we've observed.
Thank you, Joel. I also want to thank Katie, Nikki, Lindsay, and Amit for being here. I want to thank you all for tuning in. I want to just reiterate, we are going to be transparent. If we have exciting news, we're going to share it. By the way, we're all looking forward to you all tuning in as we do Artemis 2 that's coming at the first part of next year. Again, our mission back to go around the moon and home. But I just want to, if I could just say for a moment, I've had the privilege of being here for roughly 2 months at NASA. And I just want to reiterate what all of you at home know, which is this is one of the most amazing, if not the most amazing institutions that America has. Some of the brightest, smartest, dedicated people that this country has doing this amazing science. And again, we're going to continue to lean into it. We're going to continue to lean into manned exploration. And it's not easy. It's really hard. But when you have the smartest people in the world on this team, working to that end, success is never guaranteed. But I feel very bullish on our future and what we're going to find and the places that we're going to go with this great team at NASA. So thank you for tuning in. We'll continue to let you know what we find, what we see, what we think as we go through this process. So thank you very much.